Okay, so for this section, we're going to be talking about exponential growth and decay, which is an extension on the exponential functions that we've been talking about in some of the previous sections. So for exponential growth and decay, these will follow the formula f of t equals a naught, so that's that a sub zero looking thing, e to the kt, or sometimes I'll just put a equals a naught e to the kt, and I'll probably be using that a equals a naught e to the kt version. Now, what's really nice about this format for exponential functions is that it is very clear to us whether or not it is growth or decay, whether it's increasing or decreasing based on the value of k. If k is positive, any sort of positive, small, large, whatever, then that is an indication that this is growth. Now, the larger the value of k is, the quicker it's growing. Now, with decay, the value is going to be negative. And again, it could be a small negative number, a large negative number, but either way, it does indicate that it's decreasing. Now, again, the larger the negative number, or the more negative that the number is, indicates that it's decreasing faster. So we'll see that later on as we process through. Now, when we're looking at exponential growth and decay, we're going to look at a couple of different things. We're going to look at a growth and a half-life and a decay setup and how these work. Now, generally speaking, when we are presented with these problems, they are going to give us a starting amount and a starting time slot. Okay, may or may not be time zero. It may be a particular year that they're working from. Now, what they're then going to do is they're going to give us a secondary amount at a secondary time. We're going to be using that information to plug in for a naught, and t. And then we are going to work to solve for k. That's our first goal, is to figure out what the value of k is if it's not already given to us. Now, based on the information that they give us, we should already have an indication as to whether or not it's growth or decay, and that should give us an indication as to whether or not our k value should be positive or negative when we're actually working through and solving this, okay? Once they've done that, then they're going to do one of two things. They will either give us another time to check on to say how much will there be at blank time, which is going to be that we're plugging in t for our equation, or they will ask when will it reach a particular value, okay, which is going to be still giving us another value for a. So we're going to take a look. So this first example is in the year 2000, we have that the population of Africa was 807 million. And then in 2011, it had grown to 1,052 million. Now, normally we would go ahead and push that to 1 billion, but for purposes of this, we're wanting to keep everything in the same type of units. So they're wanting us to keep everything in this millions quantity, okay? So they want us to use an exponential growth model in which t is the number of years after 2000, and that'll come up important here in just a second to find an exponential growth model. So let's take a look. So I've got my information over here. I've got that in 2000, we were at 807, and in 2011, we were at 1,052. So first off, our time is going to be 11. Okay, so again, we're going to use our formula a equals a naught e to the kt. Okay, a naught is this starting amount, so that's going to be this 807. So we're going to go ahead and plug that in. E, k. Now, a is going to be this 1,052, and then t is going to be our 11 from up here. Okay, so the first thing that we're going to do to try and solve for k, noticing that it's up here, is I need to get rid of this 807. So I'm going to divide by 807 on both sides, and I'm going to save and keep all my math for the end. And I'm going to go ahead and make that 11k up there. Now, once I have this, we know that in order to get rid of the e, we can use natural log. So I'm going to do natural log of 1,052 over 807, natural log e, 11k. And again, that natural log and e are going to cancel each other out. So now I have natural log of 1,052 over 807 is equal to 11k. And then I'll divide by 11. Okay. So then I've got k is, and then we're going to put this on a calculator. Now, when we put this on a calculator, and we run it out to 4 decimal places, I get 0.0241. So now my equation that I would then use is, I'm still going to have the A. We're still going to be using that 807 as our starter. I'm going to have E. Now, my K is 0.0241, and then I have a T. So there's my equation that I'm going to be utilizing for any other further questions that they ask. Okay. So now let's go back and look. Okay. So now the next part of this says, by which year will Africa's population reach 2,000 million or 2 billion? And again, the use of the 2,000 million here is solely because since we worked this in using that 807 million to start with, we are needing to utilize the same units as we go. Okay. So I've transferred some of that over here to my screen, to my board. So we got, this is our equation that we had from the first part. Now again, I mentioned that they would ask one of two things. One is this example that they given us, what year will it reach a particular amount? The other option that they could have asked would have been, what would be the population in, say, 2015? If that were the case, then T would be 15, keeping in mind that time is since 2000. And I would just plug 15 in for this. But they want us to find out in what year we'll hit 2,000 million. So these steps are going to feel very, very similar to the ones that we had when we were solving the first time. Because again, what we're needing is locked up here in our exponent. So we're going to start by doing our divide by 807. So I've got 2,000 divided by 807. I'm going to take a natural log on both sides. Again, I'm going to save all my math to the end, just so that I can be as accurate as possible. Again, that natural log and E are going to cancel off. So now I've got natural log of 2,000 over 807.0241 T. I'm going to divide by that 0.0241. Okay. And so when I put that in on a calculator, I'm going to get T. Now keep in mind, again, T is years since 2000. So when I ran this out, I got 37.66. Okay. Putting that with our year 2000, this will either be 2037 or 2038. There could be an argument for, does this 37 represent the beginning of 2037, which means this decimal is inside of the 2037 year, or does this 37 represent all the entirety of 2037 and the 0.66 is then rolled into the next year? We also have some rounding concerns there as well. So now we have that this is going to be either 2037 or 2038. Either one would be considered acceptable. So now let's take a look at another example. And so for this one, they have been nice enough to go ahead and hand us the entire example as to how this happens, okay? So we found the exponential decay model to be A equals A naught e to the negative. There's our first indication that it was a decay model, is because it has a negative value up there for K. If there were originally 60 grams, how long will it take for strontium-90 to decay to a level of 10 grams? Okay, so now a couple things that I want to make mention here. They were nice to hand us this. Now, I am very aware, okay, that when they do these, sometimes when they don't set this up for us, they will say something like the half-life. Okay, now keep in mind what half-life is. If I have 100 grams of something, after one half-life, I will have half of this amount. So I will have 50 grams. After one half-life or another half-life, it's not all 50, it's half of this. So I would have 25 grams. Okay, And then after another one, I would have 12.5 and so on. Now, oftentimes, okay, they will mention just that the half-life of something is 20 years. So the way that I would actually do this before we start on this problem is I would say something like I have 100 grams, I have 100 grams, 50 were left after 20 years. And so I would work that out that way so that I could figure out what the K value would need to be. Again, picking values that work well with half, okay? And then once I had this figured out, okay, and let's say that they had 40% of a sample left, then I could use 40 out of 100, E negative, whatever this was, okay? So utilizing numbers to help make this a little more concrete can be helpful. So for this one, they mentioned that we had 60 grams originally. So we'll put our 60 right here. And we had 10 grams left when we were done. So again, this is very similar to our Africa example. We're just using a negative exponent. So again, I'm going to start by dividing by 60. Now, I am going to clean that fraction up because that is 1/6. I can make that nice and clean. Negative 0.0248 t. Next thing is I'm going to take my natural log on both sides. Again, natural log and e cancel each other out. That's our whole point of that. Now I'm going to have natural log of 1/6 equals negative 0.0248 t. And I'll finalize by dividing off that negative 0.0248. And so I get t is going to be 72.248. Now, I don't know whether that is in days, weeks, months, hours, years, because they didn't give me an indication as to how they got the original half-life, okay? If we were given what that original half-life time frame would be, then this would be in the same time frame.